Chapter 7, absolute value functions and reciprocal functions. So the first thing we're going to look at is absolute values and absolute value functions. This is a short chapter. There's only about 5 lessons in this chapter, so it won't take very long to get this chapter done. So if we start off with what absolute value is. The absolute value of a real number can be defined as the principal square root of the square of that number. So the absolute value of 6 would be the square root of 6 squared, or the square root of 36, which would just be 6, because 6 would be the principal square root of 36. If I'm looking at the absolute value of negative 6, I take negative 6 and I square it, I get positive 36. The principal square root of positive 36 is 6. That is the definition of it. Simply put, the absolute value of a number is the positive value of the number. So, or the other way of looking at it is it's just the value of the number without a sign. We don't worry about positive, negative. They're basically all positive. There's no signage. So for a real number A, the absolute value of A is written with 2 bars on either side of it. So the absolute value of 6 is equal to 6. The absolute value of negative 6 is also equal to 6. And the other way that you can look at it is the absolute value of a real number can be regarded as the distance of the number from 0 on a number line. So positive 6 is 6 units away from 0. And negative 6 is also 6 units away from 0. So 3 different definitions of how we can define absolute values. The absolute value of a number will never be negative, although when we work through the expression itself could become negative because of other operations that occur in the expression. So if we look at class example number 1, what would be the absolute value of 3? 3. And the absolute value of negative 3 would also be 3. What would be the negative of the absolute value of 8? It would still be negative 8. Think of this, if you have to, as negative 1 times the absolute value of 8. And then what would be the negative of the absolute value of negative 8? It would still be negative 8. So now if we look at E, we have an operation. The absolute value of negative 7 plus the absolute value of 7. So the absolute value of negative 7 is 7. And the absolute value of 7 is, and 7 plus 7 is? In F, think of the absolute value bars as almost being like brackets, so I'd have to do what's inside first. So 1 minus 5. So I would have the absolute value of negative 4, which is equal to 4. And then the last one, I have the negative of the absolute value of the negative of the square root of 81. So start from the inside and work your way out. The square root of 81. So now I have the absolute value of negative 9, which is 9. And then the negative on the outside would make my final answer negative 9. So 5 or 6 minutes to do those questions, and then we'll move on to functions with absolute values. Okay. Investigating the function of the absolute value of x. So it says, consider the functions g of x and h of x, where g of x is equal to x and h of x is equal to negative x. And the graphs have the equation of being y equals x and y equals negative x. If you remember from last year and from even earlier in the course, this is just function notation. So we call the function g. So instead of writing y1 equals, we can call this g of x, so the function g. This becomes the function h. So if we were to sketch and label each graph on the grid below, if we start off with our g of x equals x or our y equals x, that means that for every value of x that I put in, the y value is the exact same. So when x is equal to 2, y is equal to 2. When x is equal to 5, y would be equal to 5. When x was negative 2, y would be equal to negative 2, and so on. So what I would get is I would get a line that would look like this. And this would be my g of x. Now if I looked at graphing h of x, where y is equal to negative x, which means if x equals 1, y would equal negative 1, because I'd substitute 1 in for x and I'd get a negative 1. So when x equals 1, y equals negative 1. When x would equal 5, y would then equal negative 5. When y equals negative 2, I'd have negative of negative 2, so I'd have a positive 2. When y equals negative 5, or sorry, not y, when x equals negative 5, I would end up with y equaling positive 5. So this time my graph has a negative slope, and it goes this way. So then I can label this h of x. So now if we were to look at the f of x function being equal to the absolute value of x. So if x equals negative 5, the absolute value of negative 5 would be 5. When x equals negative 4, y would equal positive 4. When x equals negative 3, y equals, when x equals negative 2, y equals, and so on. So plot the points from this graph. What do you notice about the graph? What are some parts of the graph that you notice? It doesn't go into the negative sides of y. Compared to what I have over here, what do you notice? As a well, if I went like this, the graphs look the same when I cover up the bottom part of the graph on the left-hand side. So what I can say is this portion of the graph right here, that was this piece over here. So it was the same as g of x when my x values were positive. And this side of the graph matches up with this part. So this side of the graph is the same as h of x when x is less than 0. And so there's some questions down below that deal with this. So explain the similarities and differences between the graphs on the grids. So the biggest difference being that f of x has no negative y values. And then I can say that f of x is the same as g of x when my x values are greater than 0. And then f of x is the same as h of x when the x values are less than 0. So question number 4 says this graph contains two straight lines. What is the equation of this line in quadrant 1? G of x, and what was the equation of g of x? Y equals x. And what's the equation of the line that's in quadrant 2? Y equals negative x. So this is important because what it means is I can take an absolute value function and I can write it in two pieces. Each piece has a different domain. So with this equation that I have here, what I can say is that f of x is equal to x when my x values are greater than 0. That was the quadrant 1 equation. And it's equal to negative x when the x values are less than 0. We call this a piecewise function because it puts the function into two pieces. This is how we can express absolute values, which helps us when we try to work with these algebraically rather than just graphically. So if we look at the definition on the next page, the definition of an absolute value function can be defined as, so f of x equals the absolute value of x, which is the square root of x squared, so it's the principal square root. And it equals x when the x values are greater than 0, and negative x when the x values are less than 0. Noticing that when x is a positive number, the absolute value equals x, and when x is a negative number, the absolute value of x equals negative x. So we're going to look at a different function. We're going to look at the absolute value of x minus 3. So it says, consider the functions g of x equals x minus 3 and h of x equals negative x minus 3, whose graphs respectively have the equations y equals x minus 3 and y equals negative x minus 3. So we're asked to complete the table of values and then plot the points on the grid, join the points, and extend the graphs. So let's start off with x minus 3. If x equals negative 4, what's the value of y? Negative 7. Negative 4 minus 3. I substitute in negative 4 for x. So when x equals negative 3, what would y equal? And when x equals negative 2? Are we seeing a pattern? What's the pattern? Going up by 1, so we can fill in the rest of the chart here. So if we plot those points, when x equals negative 4, y equals negative 7. So there's my equation. I'm going to join those points with a line, and I'm going to label that line g of x. So now I'm going to look at the next graph. The next graph is negative of x minus 3. So if x equals -4, in the brackets I'm going to get -7, which when I multiply by a +7, I will get, or sorry, when I multiply by a negative, I will get +7. When x equals -3, in the brackets I'll get -6, and the negative of -6 would equal +6. And this pattern continues so that when x equals 3, 3 minus 3 is 0, and -0 is still 0. Then when I get 4, 4 minus 3 is 1, multiplied by the negative outside the brackets gives me a -1, and then -2. So now let's graph these points. So when x equals -4, I now have a +7. So that's h of x. So now on the right-hand side, we will draw the graph of what would be the absolute value of x minus 3. Which means, when I put 5 into this equation, or sorry, not 5, -5, I get -5 minus 3, which is -8, and the absolute value of -8 is positive, or just 8, right? And then when I substitute in -4, -4 minus 3 is -7. Absolute value of -7 is 7. So this is going to go down. And then when I get 4 minus 3, which is 1, and the absolute value of 1 is 1. When x equals 5, 5 minus 3 is 2. Absolute value of 2 is 2. So then if I go to graph this, -5 and 8, and I get this V-shaped type graph again. So again, what do you notice about this graph on the right-hand side? Yeah, there's nothing below the x-axis in this case. This part of the graph matches to the stuff in blue, which was -x minus 3. And this part of the graph matches up to the part of the graph that was in green, which was x minus 3. So if I was to write this into pieces, so the function has been written below as a piecewise function, but the domain piece has been removed. So f of x equals x minus 3. This is the x minus 3 graph. When does this graph equal the stuff in green? For what values of x? Okay, so greater than 0, does the graph match down here? It's this part. When does this part of the graph match up? When it's greater than 3. Anything less than 3 does not match up on the green graph. So if x is greater than or equal to 3, I use this graph. And then for the values that are less than 3, I use this graph. which is my negative x minus 3. So this would be for all the values that are less than 3. And I can't have it equaling both, so we usually always let it equal the positive end. So we get the greater or less than and equal to. And then the second piecewise is just the inequality. There's no equal to it. So it says, explain how the equation of the second piece could be determined from the equation of the first piece. In other words, if the equation, so for example, if the equation of the first piece was x plus 3, what would be the equation of the second piece? Negative x plus 3. So what did you do to get the negative of x plus 3? We took the negative of the entire expression. So to get the second piece, you would take the negative of the first equation. And then number 5 says, explain algebraically without using a graph how the domain for each piece could be determined. So if we go back, what is so special about positive 3 on the graph? When the x value is equal to 3. Where is that along this graph? The x-axis, what do we call this? A 0. It's the 0 of the function. So to find the domain, or how the domain piece would be determined, we would find the 0 of the function That would be our first step. And let's say if we called it P. P being some value. It could be 4, it could be 8, it could be negative 2/3, whatever that 0 is. Then the domain pieces would be that x has to be greater than and equal to P, or x would be less than P. Okay? The note, every absolute value function can be defined in these pieces. The absolute value of the quantity is always the same as the quantity if it is positive, and it's the opposite when the quantity is negative. And being able to write these in piecewise is important. We have to be able to write them in piecewise in order to solve these algebraically. So that's what we're going to practice with in the last 2 examples. We're going to express these 2 functions, absolute value functions, in piecewise notation. So when we have our function f of x, so f of x equals the absolute value of 3x plus 2, in piecewise notation we would say f of x is equal to, and we would use those curved brackets, and those curved brackets actually stand for the set of. So the set of 2 different equations. The first equation is the positive value. So it is whatever the quantity is inside the absolute value. I just take the bars off. The second equation is the negative of the first one. So negative 3x plus 2. And then I need my domains. Well, it's equal to this as long as my x value is always greater than 0. If my x value is equal to 1, it's just going to equal 1. If it's equal to 5, it's just going to be 5. So as long as this part in here, this 3x plus 2, is greater than or equal to 0, I will be okay. If it's not equal to 0, such as I put a value in here and I get negative 5, then I need to use this equation because this would become negative of negative 5, which would give me my positive 5, which matches up to the absolute value. So if my value inside the bracket is negative, I have to use this equation because that's how I cancel the negative out. Does that make sense with that explanation? Canceling the negative out. So if 3x plus 2 is less than 0, I'd have to use this equation. And then I would clean this up. So my 3x plus 2 would stay the same, but then I would actually list this off as a 0. So if 3x plus 2 is greater than or equal to 0, what is x greater than or equal to? So solve this for x. So what would I do?
Move the 2 over.
And then?
Be -2.
And then divide by? So as long as x is greater than negative 2/3, this is the equation I would use. If the equation is, if x is less than negative 2/3, the equation I'd want to use would be this one, which would be negative 3x minus 2. Okay, so we'll do one more. So again, piecewise form. So we can call this g of x, or h of x, or p of x, or f of x. G of x equals, I have my two pieces. The first piece is always the exact same as what's inside the absolute value bars. I just remove the bars. Okay, 4 minus x. And this works when 4 minus x is greater than or equal to 0, because it's positive. So as long as this value in here is positive, it will be the same as the absolute value of this one. If it is negative, so if the value in here is negative, I would have to multiply the equation by a negative. So I'd have negative 4 minus x. And that would be for values when 4 minus x is less than 0. So then I need to clean this up. So when I go to clean it up, it means that I remove any brackets. So 4 minus x would stay the same for the first function. The second function would become what? Negative 4 plus x. And then I actually state my zeros. So with this one here, do I want to move the 4 or the negative x? Move the negative x over, and I would actually write it as that. How would that read? How would I read this? X is less than or equal to negative or to 4. So if I wanted to, I could erase or I could rewrite it in that form. X is less than or equal to 4. So we read it from the variable. And then when I go to solve this one, I get that x, oops, sorry, I did that wrong. I'd I'd move the x to the other side. And how would I read that one?
X is greater than 4.
X is greater than 4, which again, I might want to erase afterwards and rewrite it the way that I would normally read it. So I'm going to give you questions 4B and 5B. Questions 8, 9, and 11.